Hi, thank you for clicking this video. In this presentation, I will talk about my work. The EM algorithm gives sample optimality for learning mixtures of well-separated Gaussians. I am Jeongyeol, and this is a joint work with Constantine. Learning the parameters in a Gaussian mixture model is a fundamental problem in machine learning and computer science. In this work, we study one important special case of the mixture of spherical Gaussians with unknown and unequal mixing rates and variances. And the well-separatedness means here that the location of Gaussian centers are separated by order of square root log k. In this problem setting, we are interested in the following question. How many samples are sufficient to recover our parameters up to arbitrary accuracy epsilon? We study this question in an information theoretical aspect. Our main contribution in this work is that in the well-separated regime, indeed kd over epsilon square is sufficient to recover our parameters. The sample complexity result also does not require the boundedness on parameters. Of course, this is an information theoretical result. We establish this sample complexity bound by showing the linear convergence of the EM algorithm from a coarse initialization. Notably, we show that EM achieves the minimax statistical rate in our parameters. We briefly give a background on the sample complexity question on the parameter estimation of Gaussian mixture models. As now it is well known that in the worst case, we must need exponential number of samples as shown in Moitra and Valiant and Haddad and Price. And in fact, the optimal statistical rate is n to the minus 1 over k at best. Since in the worst case, the centers of the Gaussian components can be arbitrarily close to each other. This rate has been established in Heinrich and Kwon recently. So what happens then if we assume that the components are sufficiently separated? So when the components are well separated, the problem becomes easier. And in particular, it becomes learnable with polynomial number of samples. And the sharp threshold of square root log k is recently established in a great work by Regev and Vijaya Raghavan. Under this threshold, we need super polynomial number of samples, whereas above the threshold, we can learn the parameters using only polynomial number of samples. And in our work, we close the gap from polynomial to linear and establish the first sample optimal upper bound in square root log k separation regime. We establish this result with our new local convergence guarantee for the EM algorithm. Now we briefly discuss the existing literature on the convergence analysis of EM. Classical results only guarantee the asymptotic convergence toward stationary points, but the recent breakthrough in Balakrishnan et al. Established a framework to study non-asymptotic convergence of the EM algorithm towards true parameters. And for a mixture of two Gaussians, it is now well understood that EM converges globally from a random initialization. However, when there are more than two components, we cannot hope such global convergence due to Jean et al., and at best, we can hope for the local convergence. And such local convergence guarantee has been previously established in Yan et al., but they required separation of root k, and their sample complexity analysis was also suboptimal. Therefore, our mission in this work was to revisit the problem and establish a tighter convergence guarantee for the EM algorithm. So in this work, we show that EM converges locally under root log k separation regime, and it achieves the minimax optimality. The high-level idea of the analysis is very simple. Here, let's focus only on the location of the first component in a balanced setting, but the idea applies to more general settings too. The EM algorithm consists of two steps. In each step, we assign a weight to each sample using the Karate estimator. And in M step, we take a weighted average. And the key property here is that when we are in well-separated regime with good initialization, most of the time the weight assigned to each sample in each step is mostly correct. Let's call these samples as good samples. We can show that EM assigns almost hard labels almost correctly. With this high-level intuition in mind, we can write down the estimation error in a closed form after one EM iteration. Now the problem boils down to bound the expectation that is shown in the first line. We can decompose this expectation into two conditional expectations, conditioning on good event and bad event. Now for good events, we know that both W and W star are either close to 1 or 0, depending on whether the sample comes from the first component or not. Therefore, delta W, you can see the definition of it in the bottom of the slide, is small, and we can control the conditional expectation on good event with this property. For bad events, we can control the conditional expectation with the small probability of bad events. This is in fact a standard proof strategy for bounding some expectations, and therefore this idea, even though it is widely used, has been often overlooked. But this is indeed the key idea to analyze the EM algorithm in a well-separated regime. As a result, we can get a linear convergence toward true parameters. Now, since we established the convergence in a population setting, we hope to connect it to the finite sample analysis. The only difference in finite sample EM is that the expectations are replaced by finite sample quantities. And we can apply basic concentration inequalities on these finite sample quantities. However, Naïve approach will give you the error of order as shown in the slide. Besides the suboptimal dependency on K, we also have a polynomial dependency on rho. This is an instance-specific parameter. For instance, it can be the maximum norm of the location parameters. Therefore, with this type of sample complexity, we also have to assume the boundedness on parameters. But we want some tighter sample complexity, which is optimal in all parameters and also does not require such boundedness assumption. So here we again exploit the concept of good event and bad event. And with that concept, we decompose each finite sample quantity into two quantities using indicator functions. Now, the technical innovation made in this work is the probabilistic inequality shown in the second blend. It looks a little bit complicated, but intuitively, it just says that for the sum of good samples, it has small variance since the variance of weights assigned in the E step is small. And for the bad samples, the average is small since most of the time the indicator function will make the quantity 0. Please check the technical details in our main paper. And as a result, we can get a clean linear convergence result with the optimal statistical rate for finite sample EM. So the analysis of EM requires the initialization. We also want to explore the sample complexity without such initialization. For that purpose, we established the lemma that when two well-separated Gaussian mixtures are pi mean over 4 closed in total variation distance, here pi mean is a minimum mixing rate, then the mean parameters fall into the region of initialization that EM requires. And from the proper learning literature, information theoretically, we know that such distribution that is close in total variation distance can be learned using order k to the 3 these samples. Therefore, we can conclude that the overall sample complexity in root log k separation regime is the maximum between k to the 3d and kd over epsilon square. We think that the first k to the 3d term is an artifact of an analysis and can be improved in the future with different approaches. Now, there are several open problems that arise. The first is that whether EM converges under even smaller separation, given good initialization. Unfortunately, the same proof strategy will not be applied, and we would need better understanding on the landscape of the log likelihood function. The second question is about the initialization. The state-of-the-art algorithms give a quasi-polynomial sample complexity with the same computational time, but it is still remaining as an open problem whether is it possible to achieve polynomial sample complexity within polynomial time. In summary, in this work, we established the local convergence of EM with only kd over epsilon square sample complexity. And the result gave the sample optimality for learning a mixture of well-separated Gaussians when the separation is order of root log k. As a future work, we are currently looking at the possibility of the local convergence guarantee under smaller separation regimes. I hope this was an enjoyable talk for you, and thank you very much for the listening.